All right, welcome back to Real Analysis. We're going to skip ahead a little bit here in Chapter 8 to Section 8.6 to talk more about functions for which this notion of integral, definite integral, or we'll call it a Riemann integral here, exists. Back in the beginning of Chapter 8 in Section 8.2, we defined what we mean by the definite integral. So its notation is over here, but we defined it only for functions that were continuous on the interval from a to b. All right. And when I say we defined it, what did we really do? We proved Cauchy's theorem. We proved theorem 8.1 that says if you have a continuous function on the interval, then there's some number that we just denote by this definite integral notation that satisfies, well, that kind of semi-complicated condition that the difference between these Riemann sums of tagged partitions and that number can be made less than epsilon, provided that the norm of the partition, tagged partition, is less than some number delta, right? So we proved that theorem 8.1, and we proved it, and the continuity of F was certainly a necessary component of the proof that we gave. Okay, we didn't talk about it, but in section 8.4 and 8.3, we talked about properties of that definite integral, and in particular, the two fundamental theorems of calculus. We skipped section 8.4, where that definition of definite integral was extended to functions that could be, well, slightly discontinuous. They could have finitely many discontinuities. I'm going to leave it to your reading if you're interested to check out what is done there in section 8.4. But kind of, in sort of sloppy language, if the function wasn't too discontinuous, then you could kind of make that work that we did in Cauchy's theorem still work. Right? You can have finitely many discontinuities on the interval and show that this number that satisfies that complicated implication in Cauchy's theorem is still going to exist. All right. So what are we going to do in this section? In section 8.6, we're going to further expand the class of functions for which we can talk about this definite integral. But this is going to be kind of an interesting approach. And instead of kind of looking for hypotheses that could replace continuity in Cauchy's theorem, we're going to and then try to prove that theorem with those hypotheses. That's certainly one way to think about what I mean by expanding the class of functions. We're going to kind of turn the tables on the whole thing. We're going to follow Riemann's idea. And what we're going to do is we're going to just say, well, let's just define some class of functions, some family of functions. And let's just make the definition be like, well, let's talk about functions for which Cauchy's theorem holds. Okay. We'll give them a name. We're going to call them Riemann integrable functions. And then we'll kind of see what we can say about such functions. So instead of kind of looking for the right hypothesis to replace continuity with, we're just going to say, well, let's just talk about functions for which that theorem would hold, and then see what we can say about those functions, calling those things Riemann integrable functions. Cauchy's theorem says that class of Riemann integrable functions is certainly going to contain the continuous functions. Okay, so let's take a look at what I mean by that. So this is kind of the main definition of section 8.6. And then what am I defining? I'm defining what I mean for a function on an interval between two numbers, a and b, to be so-called Riemann integrable. Okay, so named after George Riemann, whose approach we're following here. So we're going to call a function Riemann integral. If you want the short version, I'm going to call it Riemann integrable on AB if it satisfies Cauchy's theorem. But the long version of that is the following. So it's Riemann integrable if there's some number, I'll call it I here in the definition, and that number has the property that if you pick any epsilon, there's always a delta. It depends on that epsilon, such that the Riemann sum on a tagged partition P differs from I by less than epsilon, and that has to be true for any tagged partition whose norm is less than delta. Okay, and we'll use the same notation as before. If such a number exists, we'll denote it by this symbol integral from a to b of f of x dx. All right, I'm going to leave it as an exercise to you to show that if such a number I exists, it's unique. So I can kind of just say that this number I depends only on f, a, and b. In fact, I'll often shorten our notation that of x dx kind of comes from sort of a calculus point of view. They're very vestigial here. I like this notation better because this number I, what does it depend on? It depends on the function f, and it depends on the numbers a and b. So why not just make the notation have those ingredients in it? This of x and dx are kind of vestigial. So I'll often just sort of omit them from our notation. Okay. And I'm going to leave it as an exercise to you to show that if such an I exists for a given function on an interval, then it's unique. There's only one value of I that can satisfy this definition. Okay, so that's what I mean by a function being Riemann integrable. And I'm going to just denote by the capital letter R of AB the set of all functions that are Riemann integrable on the interval from A to B. So back to the kind of intro of the lecture, we're going to just take this as a definition of what's in this set. And then we're going to kind of start saying like, well, can we study functions? What could be true about functions that are in this set? All right, so we're going to be studying Riemann integrable functions. We already wrote this above, but I'm just going to say it one more time. In this language, Cauchy's theorem, that theorem 8.1, just says that if f is continuous on this interval, then f is Riemann integrable. So that set R of AB contains all the continuous functions on the interval. Okay, so what else can we say? Well, differentiable functions are continuous, so R of AB contains all the differentiable functions on the interval. All right, so that's kind of what I mean. I'm just sort of trying to make you curious about like, well, what's in this set? We know some stuff. Any differentiable functions in there? Any continuous functions in there? I wonder if there are functions in there that are different. What's in this set? Okay, we're just going to give it a name. So I'm going to make this lecture kind of short. I'm just going to kind of try to show you an example of a function that's not in this set. And then I'm going to show you an example of a function that is in this set. And certainly we know that any continuous function is in there, any differentiable function is in there. So when I show you the example of one that's in here, it might surprise you. It's not going to be continuous, not continuous on the interval. Okay, so for our first example, let me take the so-called characteristic function on the rationals. All right, so I'm going to define a function. I'm going to just make the set the interval from 0 to 1 for concreteness. You can do this on any interval that you like, though. And let's define the value of this output of this function to be 1 if x is rational and 0 if it's not. So that's the so-called characteristic function on the rationals. And I claim that that function is not Riemann integrable. It's certainly not continuous. In fact, we proved earlier in this course that this function is not continuous at any point in the interval from 0 to 1. It's so-called completely discontinuous. It's discontinuous at every point in its domain. And I claim it doesn't have an integral. Okay? So how am I going to show that something is not integrable? Well, I have to kind of show that it cannot satisfy the definition of Riemann integrable. So let's take some delta, right? So take some delta and take some partition whose norm is less than delta. Any partition. So partition the interval from 0 to 1 to a bunch of subintervals. The max length of any one of them is less than this number. Delta is an arbitrary positive number. Okay, well, by the density of the rational numbers, I could always tag that partition by choosing rational tags. Every subinterval in that partition contains rational numbers. I can pick a rational number for its tag. And if I did that, and then I looked at the corresponding Riemann sum for the tagged partition, is my dot big enough there? Well, the output of any one of the tags is equal to 1 because I picked all rational tags, and I multiply 1 by the length of the intervals, and I sum over all the intervals. Well, summing 1 times those interval lengths over all the intervals is just going to be the length of the total interval. I'm going to get 1 minus 0. That's going to give me 1. So if I take any partition of length of norm less than delta and I tag it with rationals, the Riemann sum for that partition is equal to 1. Okay, doesn't matter how I choose the tags as long as I choose them to be rational, and it doesn't matter what delta was. Okay, well, compare that to take that partition of norm less than delta and choose all the tags to be irrational. This is also possible. Every interval contains irrational numbers. Well, the Riemann sum for such a tagged partition, the output of every irrational number is zero. Zero times the interval length is zero, so that Riemann sum is going to be zero. Okay, so to recap, for any delta, if I take a partition of norm less than delta, I can find some tags that make the Riemann sum 1. I can find some tags that make the Riemann sum 0. All right. Well, that means if I took, say, a number epsilon to be less than the distance between 1 and 0, I'm going to be kind of specific here and choose the number epsilon to be 1/2. So if I take epsilon to be 1/2, then no matter how I choose delta, I can find a tagged partition of that interval whose Riemann sum will differ from any number by more than epsilon, by more than 1/2. I'm going to kind of leave the details to you there, but for example, if the number I was, say, bigger than or equal to 1/2 in absolute value, then I would use those irrational tags because I'd have a 0 here and I would get that that difference is bigger than 1/2. If I were less than 1/2 in absolute value, I'd use the rational tags, and then 1 minus I is going to be greater than or equal to 1/2. All right. So there's some logic. I'm going to kind of be a little bit vague here, but that's something for you to think about. But this function cannot possibly satisfy the definition of Riemann integrability for any number I. Okay, so if it can't satisfy the definition for any number I, well, then it's not Riemann integrable. It's in some sense too discontinuous. That's a vague, fuzzy thing to say. But this function kind of has too many discontinuities for it to be integrable. If you study this notion of Riemann integrability more carefully, that statement can be made precise in a very specific way. But we won't have time to study these notions in this course. Maybe in the second semester we can bring that topic back up. Okay. So you're saying like, yeah, okay, so it has too many discontinuities. Well, let's look at an example of a function that's got, well, quite frankly, quite a few discontinuities, but it is Riemann integral. Let's remind ourselves about this Thomae's function. I'm going to denote it by h, and not t for some reason. But how did we define h? Do you remember how it works? H is defined on the interval from 0 to 1. If you take a rational number in lowest terms, that's what that greatest common divisor. So some rational number p over q in lowest terms, then h of it is 1 over q. If that rational number is not 0. If the rational number is 0, I'll just say h of it is 1. And then if you take an irrational number, h is 0. So maybe I can kind of recall to you over here. Let me just sort of move this so I have a little bit of room. Recall that we proved that h is continuous at every irrational number. But it's discontinuous at every rational. So it's got a lot of discontinuities. It's got countably infinitely many discontinuities in the interval. But I claim that it's Riemann integrable, and in fact, its integral is 0. Okay. So I'm going to kind of walk you through an argument here. There's a couple places in the argument where I'm going to leave some questions to you so that you can stop the video and try to answer them. They're reasonable questions, and I really encourage you to stop when I ask you why something's true and see if you can puzzle it out. Okay. So let me try to convince you that this function is Riemann integrable and its integral is 0. So using our brand new definition of Riemann integrability, let me have some positive number epsilon. And I'm going to start by defining a set. I'll denote it by E sub epsilon. And it's just those inputs such that H of them is at least epsilon over 2. Okay. So the first question that I'm going to have you stop the video and puzzle over is that's a finite set. That's a finite set. So I'm going to leave it to you to think about why. But there's only finitely many points in the integral where h is bigger than epsilon over 2 for any positive epsilon. So I can talk about the number of elements in that set. I'm going to denote it by n sub epsilon. The spirit of this is that, epsilon's supposed to be small. So without loss of generality, I can assume it's less than or equal to 2. So 0 is always in this set, E sub epsilon. H of 0 is 1. If epsilon's less than or equal to 2, 0 would be an E sub epsilon. So E sub epsilon isn't empty. It has at least one point in it without loss of generality. Okay, so there's the first step. Second step in the argument, I'm going to define my delta. I'm not showing you the backstory on this, but I'm going to say, let's let delta be epsilon over 4 times that number, n sub epsilon. Okay, it's a positive number. And then take a tagged partition of the interval, 0 to 1, I mean, and call the tags c sub k, and suppose that the norm of this partition is less than delta. Okay, got a positive number delta here. I can always choose a tagged partition. I don't care how you pick the tags, just pick them in the subintervals, make the norm less than delta. Okay, and then I'm going to kind of split this partition into 2 parts. I'm going to say that P1 contains the subintervals, the endpoints, the same thing of the partition P, where the tags belong to our set E sub epsilon. All right. So you look at all the subintervals in P, and one at a time, you ask yourself, is the tag in E sub epsilon? And if it is, you throw that subinterval into P1. Okay. If it's not, you throw it into P2. P2 is the remaining subintervals. So those tags aren't in E sub epsilon, right? And it's obvious that the Riemann sum for H over that partition P would consist of the Riemann sum of H over P1 and the Riemann sum for H over P2, although P1 and P2 are not partitions of the interval from A to B. So maybe it's a little sloppy to call them Riemann sums, but the union of the intervals in P1 is probably not the entire set A to B, and nor is P2. So by this Riemann sum notation, I just mean take the tags, plug them into H, and multiply it by the corresponding. But I'm just saying, if you did all that for the things in P1 plus all that for the things in P2, you would certainly account for everything. Good. Okay. Here's your next chance to participate here. There are at most 2 n epsilon subintervals in P1, right? Not n epsilon. There's at most n epsilon points in E sub epsilon. But a point in E sub epsilon could give rise to actually as much as 2 subintervals. It depends on where the point is. So I'm going to leave that to you as a detail to think about. But there's certainly no more than 2 n sub epsilon subintervals in P1. And every interval in this partition has length less than delta. So all those things have length less than delta. So if you summed the lengths of the subintervals in P1, so you add up all those lengths, then, well, you would get something like what? That would be less than the number of them times the length of each one. And we wrote in that delta is 4 over n times, or 4 over epsilon over 4 times n sub epsilon. Sorry, it's too hard to pronounce all of these things. And here's our 2 times n sub epsilon, and that simplifies to epsilon over 2. I should have just shut up about it. All right. And if you take a tag in P1, well, it's in this E, it's in this E sub epsilon. So H of it is bigger than epsilon over 2. So first of all, that tag can't be irrational. So H of it is positive. But Thomae's function never outputs anything bigger than 1. So for all those tags, H of them is positive, but less than or equal to 1. So if we looked at that sum, I'm going to keep calling it a Riemann sum over just P1. Well, if we replaced all of the outputs H of epsilon sub k with something bigger than them, we would make the sum bigger, replace that with 1. Once we have a constant there, that sum would just add up to the lengths of the subintervals involved, and we said that that's epsilon over 2. So we get that sum over the subintervals in P1 is less than or equal to epsilon over 2. It's actually strictly less than it, but we can leave it less than or equal to. It doesn't matter. Nice. Okay. Well, kind of thinking along the same lines. If you sum the lengths of the subintervals I left out the word lengths here. Sum of the lengths of the subintervals in P2, that would certainly add up to something less than one. One would be the sub over the length of the subintervals over the entire partition P. And in P2, I know that because the tags are not in E sub epsilon, well, then H of them is actually strictly less than epsilon over 2. Yeah, I can make that a little bit more precise. It's strictly less than epsilon over 2. Okay, that's because the tags can't belong to E sub epsilon. So using the same reasoning that the sum over just the subintervals and tags that are in P2 is no more than the maximum function value there times the length, well, that's also epsilon over 2. Sort of play different roles, but the result is the same. So finally, if we look at the entire Riemann sum's difference from 0 in absolute value, well, that's certainly just the absolute value of the Riemann sum. H is a non-negative function, so that Riemann sum is greater than or equal to 0. The absolute values don't do anything. We already remarked that Riemann sum splits into these sums over P1 and P2 separately, and we just argued that those things are less than epsilon over 2, respectively, and that sums to epsilon. So what have we done at the end of the day? Given an epsilon, we defined a delta so that if you take any tagged partition, P, whose norm is less than delta, then that Riemann sum differs from 0 by less than epsilon. So first of all, that shows that the number I equals 0 exists in the definition of Riemann integrability, so that H really is Riemann integrable. And as a bonus of our calculation, the integral value is 0. All right. So this is surprising. We kind of got a little bit of a glimpse that this set of Riemann integrable functions contains, well, maybe this is a surprise. This is a function. It doesn't just have finitely many discontinuities. It has infinitely many discontinuities, one at every rational number. But its integral still exists and equals 0. Okay, so that's where we'll end this. Thanks for listening.